All right. Um, so this session we'll talk about extension headers and explicitly saving them. There's a reason why I'm going to use the word saving. So a little bit of background. If you're not familiar with the whole world of extension headers, these are mechanisms, protocol constructs that are supposed to make IPv6 extensible. And a little bit of history. Way back in the day when they created IPv4, the idea was IPv4 was variable length header and could accommodate some number of options, I guess about 40 bytes of options. So options are basically a list of TLVs that are type length value. The idea was we can put generic network layer information into these packets, and they would be processed not just by the end node, but also within the network. So we can do source routing, time stamping at intermediate nodes. Two cases. So IPv4 extension headers, they were, I think, and by any standard, an unmitigated failure. Problem was router vendors, when they saw this, they really don't like anything complex, and they viewed having to process variable length headers as super complicated. The other problem was there really wasn't any useful option, generally useful. There were some cute ones. I remember back in grad school, how amazing it was to do record route, but it turns out they really aren't that useful. So IPv4 options, they kind of died on the vine. And there was a famous paper called IPv4 options aren't an option, but they're pretty much DOA. They're not going to happen. So IPv6 came along, and great, we have a chance to do a complete do-over. So why not in IPv6? Let's reinvent everything. So they did something that was, pretty smart actually. They made IPv6 fixed length header, took the options out of it, and what they did was they created this concept of extension headers, which are protocol headers in themselves that lie between the IPv6 header and transport layer header. So that's good. In a sense, that solved the problem of variable length headers. So now everything's fixed length, or at least the IPv6 header. But the problem became it's still viewed as complex to particularly router vendors. So a lot of them have made shortcuts, and in some cases they outright refuse to process packets with extension headers, so we have a large drop rate on the end. In other cases, they do process them, but they relegate them to the slow path. So there are some different types of extension headers of different levels of usefulness. Routing headers are kind of unique. They replaced the source route option in IPv4. Now we have an explicit routing header that can do routing per hop routing. So segment routing, for instance, SRv6 uses that. Authentication, IPsec, those are actually critical in use. So those were also extension headers. Fragmentation actually was something that was in the core IPv4 header, but of course that became an header in IPv6. Those were kind of useful options to a varying degree, but the more interesting ones, at least for this discussion, are kind of the hop-by-hop and destination options. And of those two, hop-by-hop options are the most interesting. This is where we still want a completely extensible IP networking protocol that can be processed by intermediate nodes for various purposes. So all of this was defined. Recently, RFC 8200 became an internet standard. And unfortunately, we're still not doing great on these. So what's the problem? So basically, deployment of extension headers been very disappointing. There are some RFCs working IETF more on, kind of hard to tell if they're just documenting the failure if they're trying to justify it. Sometimes having this conversation a little bit interesting. But the fact is, measurements on the internet going back to, I guess, about 10 years ago, there's still a lot of basically firewalls that are dropping packets. And this creates a problem because now whenever anybody comes up and says, oh, we need an extensible protocol network layer, use IPv6, and we post that, then inevitably, well, this RFC says they're not deployable, therefore we shouldn't use them. Great, but we lost something. So fundamentally, that kind of creates what I call the chicken and the egg problem. So operators, they do what they do. They will drop extension headers. In particular, they will drop hop-by-hop options. It's a conservative security model, and it's kind of hard to argue against that. And their argument or justification is, look, nobody's using these. They're not useful. So therefore, that's at the best case, they're a liability. So a lot of them do drop them. The loss rates vary from 70% or 30% to 10% on the internet. So, like I said, hop-by-hop options are actually a little worse. The original idea was every node in the path has to process them. That's a problem because now every router thought they had to process them. So they created its own mess, just that one requirement. But the other side of the chicken and the egg problem is, well, protocol developers aren't exactly encouraged to develop new useful options, extension headers, if they're not going to be deployable. So how do you break this cycle? We want to develop new protocols that are useful, but if we do, they aren't deployable. Granted, there's some examples of this. I mean, Quick was able to do this, but on the other hand, Quick had a giant hyperscaler behind them pushing it on the vendors who reluctantly agreed to allow UDP port through. But it's not just this security model that's the problem. There's this other aspect, which is the pragmatics of routers and switches. And the way to understand that is, like it or not, there's sort of this implicit requirement on a lot of devices in the internet, a lot of intermediate routers, that they have to be able to parse transport layer header. It's their requirement to do filtering. Now, if you look at any RFC, RFC 8200, there's no requirement anywhere, except maybe for NAT, that you have to have intermediate devices do this. Yet they do, kind of the pragmatics of working on the internet. So when they do this, they have to be able to parse into transport layer. And if they don't, a lot of times they'll just drop the packet because it's a security hole. They can't figure out the TCP port, then they don't do that. So they do have capabilities, obviously, to do this parsing, but the fundamental problem is when we put extension headers in the packet, that pushes transport layer deeper in the packet. Now, there's a lot of hardware out there that's incapable of reading that deep into the packet. It's a common hardware router design. They have this so-called parsing buffer, pulls off n bytes of the packet, where n could be 64, 128, some of the newer routers, 192, 256 bytes. Obviously, the more the better in that sense, because I can go deeper into the packet. A lot of devices don't do this. We actually see in some of the data that size does matter. If I have large extension headers versus small ones, I can push the transport layer too deep in the packet, see packet loss increase with more extension headers. Hence, conclusion is because of the size. A little tricky. Also, one thing I would point out, vendors like to be kind of cagey on exactly what their policies are, and actually operators too. Kind of this odd thing. We ask them what they're doing. well, there's security issues or this and that, competitive issues. So a lot of this we have to kind of derive from the data, and fortunately, sometimes the data doesn't like it. So the other problem that we see, and this is really where I want to get to today, since we want to try to circle around to Linux, there are just a whole bunch of implementation issues around this. These things have existed for, 20, coming up on 30 years. We've known about the problem for 30 years. They've actually been in Linux supported, which is good for about that long of time. But kind of like anything else, if they're not used, they're not relied upon, bit rot takes over and it's buggy. And in fact, it's really easy to find bugs in Linux around extension headers, especially when you get into some of the hardware offloads. Let's say Eric here, but he had a great example. Just last week, he found a bug, and I think Justin's going to regale us with some of his findings about this. So the code is buggy. Some of it has to do with hardware, maybe some doesn't, but yeah, we know there's some bugging. Another problem, the APIs are pretty miserable in a sense. Have to have root privileges to use these. Very restrictive model in Linux. Kind of implies that these are narrow use case. And some of the things we want to do with extension headers in IETF is really open this up to make it more generic. We want more interaction with the transport layer. One of the things we want to do, for instance, is we're going to gather telemetry from each route on the path, call that IOAM, and incorporate that back into the transport layer to do better congestion management. It becomes difficult when the APIs don't allow an arbitrary program to do that. And so we need to fix that problem. The other one that becomes really obvious when you start thinking about it, and it amazes me that we haven't seen this problem turn up, which I guess could only be because these aren't widely deployed. What we have now in Linux is incredibly obvious denial of service problem. Linux follows the RC8200 very well. That's kind of a problem. Because when they did extension headers versus IP options, the idea was, oh, we don't want to have limits. Let's allow you to fill up the whole packet with extension header. And let's allow a single, like a hop-by-hop option or destination option. Let's allow them to have like 700 individual options. Okay, 700. Now they also did this one other great thing. Let's allow, if the host doesn't know the option, let's allow them to skip it. Go to the next one. That's great. Now I have backwards compatibility. I can put as many of these options in as I want. The world is my oyster, everything. I have all the functionality I want. What's the problem with this? That's the definition of a denial of service attack. All you have to do, you can literally, the attacker put 700 options to twiddle the bits, set the high order 2 bits to 0, which is ignore, pick some obviously unknown type, repeat that 700 times, send that to a Linux device, IPv6 stack, parses it all. I've had this argument in IETF, and these people don't comprehend the fact that CPUs and software have denial of service issues. Like, no, only hardware does. Okay, what's involved here? This isn't just loading the data from cache. This is TLV processing. I have to actually look at each type, look it up in a table. I have to check the length, like a whole bunch of stuff just to skip it. It's a huge amount of work. So it's an obvious denial of service attack in hardware and software. Hardware guys figured this out, believe it or not. that whole parsing part, that actually limits it. But yeah, it's a major issue with software. So this will be the last part of my part, and then hopefully get into some discussion about some of the other findings and some of the discussion about the state of the world. But my view, we need to fix these. There's a mentality, use it or lose it. If we don't fix these now, if we just keep putting band-aids over this, finding workarounds, accepting myopia from the vendors, if we don't need to fix it, we'll lose it. We will wind up with, for the next 50 years, a network protocol that we can't extend, and we have to do a whole bunch of hacks because the need for this sort of mechanism is there. This is honestly, the only correct way to do it. So we know this, and fortunately, a lot of this does have to begin in IETF. IETF created these. They created the open-endedness and kind of the invitation for the denial of service attack. So there's two key drafts now. Both of these are well into the way. I think the hop-by-hop option should be going to IESG soon. This is the one Bob Hendon led. He's kind of like a long-term IPv6 expert. But basically, hop-by-hop options just need to undo restrictiveness of that. And one thing is, and this is so critical, but it sounds so simple, routers now ignore hop-by-hop options completely. If they would have just said that in 2460, the world would be completely different. You don't have to process these. You can ignore them. Don't put them in the slow path and kill everybody. Just ignore them. So that was a big win. But the hop-by-hop options processing takes that farther. So now we describe how you can ignore them. You're allowed to process a subset of hop-by-hop options and ignore the rest. And as long as everybody understands these rules, then we're good to go. The other one actually is a draft that I have done. And this is to address that denial of service problem. So we need to have limits on open-ended protocols. Sounds kind of contradictory, and some people think it is. But if you want to save extension headers and get people to use them, you actually have to limit their use. So it's kind of weird when I say it, but it's true. 700 options, hop-by-hop options in a packet is the only use case is denial of service. I don't see any other way around it. Okay, 700's up here. 0 is down here. Now here's the trick. Where do I find that number that satisfies extensibility and is future-proof? But above that, it's obviously a denial of service attack. This is a meta problem always in protocols, right? Sometimes we have to set an arbitrary limit, or at least recommend one. There's no formula for it. We have to take a best guess. So that's what we do in this draft. We actually take some best guesses. I'll give you an example. So one of those best guesses is we recommend that all hosts and all routers, if they process options, can process 8 of them in a single packet. Now, there's some logic behind that, but good news is 8 is a lot less than 700. And it's more than 0 and more than 1. So it's a reasonable trade-off, and there's some hardware reasons to do that. So the other one, though, which is a little more
is that the first 8, or is that some 8 that I choose?
That is a very good question. It has to be the first 8. Now, there's a whole bunch of crazy nuances here. Is padding an option? No, padding's not really that interesting. But on the other hand, there's already rules about padding. So Linux actually did a really good thing. Linux has some pretty restrictive rules about padding. So I think even before IETF figured it out, no one ever needs more than 7 bytes of padding. So easy to make those rules. So what we're talking about here is 8 non-padding options. And it's a recommendation. You can follow it or not. But when you're sending, if you want to have the highest probability of success, our recommendation is use 8 or fewer options. And that, we think that's reasonable. The other one is going back to this concept of the parsing buffer. This is a little more, I guess, invasive or potentially controversial. So we did the math, and our recommendation is that parsing buffer includes, say, the Ethernet header, IPv6 header, extension headers, and probably the first 8 bytes of transport header. That recommendation we made is 128 bytes, which means 64 bytes of extension headers. The reason that's controversial is because this is an actual should on device development. Now, my argument is pretty simple. IETF never, and nobody ever gave these guys guidance on how much data they have to parse. Everybody's pulling it out of a hat. So this does kind of demand to have a universal recommendation standard. And it would only apply to those devices that need to parse into the transport header. But that's the recommendation, 128 bytes. That was based on some data, found that seems to be the sweet spot. There are already a lot of devices that support it. So that's kind of like at a protocol level what we're recommending. In interesting use cases, those are actually coming up. Talked about fast last Netdev, so that's a really good example. There's also segment routing, IOEM, a whole bunch of things. So are any of these going to become vital to the internet such that they're like TCP options and they have to be parsed? Probably not. But we do know, at least SRv6, good example of getting some traction. Also, fragmentation is kind of amusing. That one comes up every once in a while. There are so many people who think fragmentation should be obsoleted. And then there's this whole other wave of people saying, wait a minute, I'm using that in my data center. You can't obsolete something and use. So not going away. It is interesting. So I would say there's enough traction on the interesting use cases that is generating significant motivation to fix these problems. So that's good news. Last part, we need to fix the bugs. I mean, the kernel has these bugs, like I said, checksum offload. I already submitted a first wave of patches to fix this. I don't know if you've seen this, Justin. I just doubt there's any device that claims to support extension headers for checksum offload that understands routing headers won't work. So minimally the routing header problem, but maybe you have some other use cases. I think Eric's use case didn't involve a routing header. Also, a while back, I think I just need to resurrect the patch set to revamp the user API. The idea was, let's allow users to set up extension headers like hop-by-hop options. As long as there's good control and control what they do, why not? I mean, not necessary. I mean, these things aren't evil. They're extension headers. So we went a little more to that. The last one, apply extension header limits. That is pending. Kind of want IETF to finish that work. They've been dragging their feet just a little bit. But once that becomes RFC, it would be fairly simple to apply into the stack. But we just need to say, look, you send me an extension header with 700 options, drop the packet. log it. I mean, so that's kind of where we are. So with that, are there any questions about that? You're smirking.
Well, I mean, you mentioned everybody drops them, so I'm just kind of wondering, why do you think they'll stop dropping them?
I did what?
Why will they stop dropping your extension headers?
Oh. You want them, I mean, are they useful or not? So the problem is, who's dropping? Not everybody. So consider you have a data path, 10 nodes. One node, they're going to drop for whatever reason. So it takes one node, means I don't get end-to-end service everyone. That's the fallacy. And that's why it's so frustrating. And it's more of a generic issue that I go round and round with router vendors. They have to stop participating in protocols above their layer. What can you do? So realistically, there will always be drops. Realistically, somebody will always be dropping UDP. But the goal here is, how do we either compartmentalize them, identify them, and one of the things I would love to see, and maybe somebody from a large hyperscaler that has the capabilities to do this, than me, somebody else, what I would love to see is a grand map of the internet and tell me what, or tell the user, more importantly, how they're being limited or not being limited by their operators. So it's a mismatch. And you know as well as I do, the fundamental problem we have being kernel and host developers and application developers. We have to develop network solutions that work everywhere. So that means fundamentally, the greatest way to achieve the success of sending stuff over the internet, especially, is to send the simplest thing you can. Don't ever send extension headers. Don't use IPsec over the internet. That's crazy. Don't ever fragment. Just send single packets. Now that's great if you think the internet's perfect, but I think it needs to kind of evolve and do more stuff. Dangerous is a relative term. So the comment was, firewall should drop everything dangerous. Dangerous is a relative term. Firewall should drop, oh, it's a separate question. Anyway, Justin, do you want to comment or? It's on. No.
Yeah. So yeah, the thing is, there is not really a use case for the wide internet, right? So what you see is that, as mentioned, if you have your network to operate, you would just drop something like this because you don't have a use case for that. So I think this is the problem, right? You got segment routing, for instance, limited domain. You got some telemetry technologies like IOM, where you collect telemetry data, or limited domain too. So hop by hop is probably for limited domain, right? I think Tom suggested some usage of hop by hop for signaling from network to host or host to network with hop by hop. That could be a use case, but again, this is the chicken and egg problem because, a lot of people dropping the extension headers makes them unusable. So that's a problem, and I don't have the answer for that.
Tom, I was a little bit confused about your thing that the router vendors should be staying out of their, stay at layer 3 and not engage in protocol violation. Is that I think what you meant? Because the question is, are these extension headers for routing in the network, in which case they're a layer 3 thing, or are you expecting people to be using them for other things higher up the network, in which case this probably gets back to what we said over here about firewalls, as I would just turn, if I didn't understand what was going on in these things, I would just have a firewall and drop it on the outside, because it's like, I don't, the combinatorics of you both routing stuff inside of networks, but potentially having layer 5 data engaged in this stuff, I think this is a security nightmare that I would run away from in spades.
So
if I was a CISO.
Yeah, I got it. So there's different types of extension headers. Hop-by-hop options they're explicitly allowed to be processed by routers and intermediates. They follow immediately the IPv6 header, so they're at a well-known location. And they can be modified in flight. So those are intended to be processed by nodes in the data path. RFC 2460, which was the first IPv6 protocol spec, they actually said that all routers have to process. That one line actually created most of the problem, because routers looked at that and their choices were either process them in the fast path at great expense and cost, process them in the slow path, which effectively will kill the utility of them because the path was like 10x worse, or drop the packet. So they didn't have a lot of wiggle room. Fortunately, in RFC 8200, they said, no, you don't actually have to process them, be configured. That kind of addresses the issue. Now, that being said, I think it's completely understandable that packets coming into my network with hop-by-hop options, it makes sense that an operator is going to drop them, because those hop-by-hop options are potentially targeting devices within its network. So that, to me, is a problem. But the argument for hop-by-hop options actually can be simplified. I don't think there's a use case for these on the internet at all. Use them in what we call a limited domain, then you should be fine, because nobody's going to have a firewall inside their limited domain dropping these. And if they're trying to use them, obviously they're not going to be dropping them. Some of the other ones, though, destination options and routing header, those are processed not by every node, but potentially could be processed by intermediate nodes in the routing list, which actually creates some interesting problems, not so much in extension headers, but just there's a little bit of conundrum what to call these things. So we know what routers are, we know what hosts are, but then we have these odd kind of things in the middle of the network that have some properties of host, some properties of router. That's why in the limits draft that I had done, I explicitly have 3 categories of processing. How does a host process these things? How does a router process these things? How does what I call an intermediate destination process these things? That last one's a little bit controversial. Some people disagree with that, but I think it's necessary because processing is different. So what you process depends on what you're supposed to process, depends on what you normally what the spec says. Now, the problem with the parsing header that I mentioned is in order for somebody to parse a transport layer, they have to go all the way through and skip over the extension header, which means they have to minimally look at them. There's a hop-by-hop option and a destination option. You have to skip over them. So that technically violates the RFC. It's a protocol layer in violation. But you have to be pragmatic. Firewalls do this on a regular basis. They do port filtering. So we're kind of stuck there. And that's why that particular limit that we set, the 128 bytes, doesn't really fit in with the rest of the limits because it's actually a limit on ICE itself. That's not, it's more, in a sense, demanding to have that limit. You need to have something. So yeah, it's not so much that protocol layer in violation. I mean, it certainly is architecturally. And I would prefer to live in a world where no intermediate devices ever looked at anything beyond the network layer. But realistically, they do. So, if there's a better solution, it'd be nice. Okay, go ahead, Mike.
Hi, can you hear me?
Yeah.
Fantastic. First off, Tom, thanks so much for doing this. This is a really important area, as you've outlined, and you've taken a very complex topic and made it almost understandable even to me. So thank you for all that you're doing, and in particular this presentation. My question is on your slide about how do we move forward, or how do we fix this? What can we do? And in particular about the 128 bytes. Can you elaborate a little bit on how that was arrived at? And the reason I'm asking is it seems low when you add the other headers in there, and is an extension header going to be 32 bytes if it is, or more? If it is, then that's only 2 of them, and is that enough? And so, just how did you come up with 128 being the optimal solution there?
The derivation of the 128 comes from both empirical data, thought analysis, and also there is some quasi-precedent in protocols. So I'll say the quasi-precedent actually comes from Quick RFC 10,000. Under certain circumstances, they actually limit the amount of IPv6 extension headers to 32 bytes. I don't believe they put much thought into that. They just started with what do we want the quick payload MCU to be, and whatever's left over you can use for other stuff besides the quick header. So it turns out in IPv4 they actually allow up to 64 bytes of other stuff. Basically, or simply because the IPv6 addresses are longer. So there's already some precedent for creating that limit. So going in reverse order, I guess, thought experiment was looking at various extension headers that have been defined. And also, we have to consider the most general case. So this is assuming, say, extension headers on the internet. How much do we really need? So let's say we have fragmentation and a few bytes of options. I think there's a strong motivation to always keep extension headers small anyway. So the analysis was, assuming a few bytes of extension headers or some hop-by-hop options, this is pretty realistic for use cases we saw on the internet. The other critical part here is, and this is true for all of the limits, these are only like baseline defaults. If I'm working in some data center and I control all my hardware, and if I want to build up an extension header that's 1,000 bytes long, you can do that. I mean, that's not an inherent limitation. But what we wanted to do was give vendors some kind of guidance for the minimum size. But the third part, which is probably among the most critical, when we got the data back, wasn't in RFC 7228 or whatever that original one. Some of the later data that people have run did show that size of the extension header mattered. There was a big drop between 64 bytes of extension headers versus 128. And that 64 bytes of extension headers compared to, say, 32 bytes was a little more, but not a lot. So the extrapolation from that data was that devices that don't drop extension headers off the bat, so there was still like 10% would drop any size of extension header. But if you took those out, what was remaining was devices that would drop based on size. The one that seemed to be the most common and still allow some utility did seem to be about 64 bytes. And if you add in 64 bytes for Ethernet, the IPv6 header, and the transport layer, you get 128 bytes. So if you look at that draft, though, limits draft, it's all there. We actually do describe the derivation of all the limits. That being said, I mean, you know, at some level, you have to pull it out of the hat. I cannot guarantee that this is perfect. That's also why the draft is not a proposed standard. It's actually BCP, although the Shepherd wants to change it to informational. So these are, in a sense, soft, not enforceable.
Okay, good answers. Good answers. Thank you. Just for clarification, is the 128, is that for extension headers, or is that for the full header chain?
The 128 bytes is full header chain.
Okay. So we're looking at 64 for that.
Yeah, we already know that a lot of devices can handle one layer of encapsulation, which you could argue is kind of part of that. So technically, we say the IPv6 header chain maximum is 128 bytes, which translates into 4 bytes of extension.
Okay, thank you again.
So if you do want to put a limit on this, put a limit on the size of the extension headers, not on the size of the entire header, because there's a lack of clarity here about, for example, whether there is an Ethernet header and whether there's a VLAN or 2 or 3 VLAN tags on top of things.
We define all of them. If you look at the extension header limits draft, there's limits on the number of options, limits on the number of extension headers, limits on the size of an option, limits on the size of an extension header. All of those, though, really critical to understand. All of those are recommendations, they're not enforceable.
Sure, but as a user, you want to be able to send a packet with n bytes of extension headers, and you don't control the path on the network. And if it goes through a VLAN and MPLS tag, and just because of that, the limit is lower.
If it does, it does. I think the best way to conceive this is what would work best on the internet. So on the internet,
Zero.
Yeah. So what would work best that would allow us some utility? So it's a non-zero number. I mean, but this discussion is just reflecting any protocol that has some variability to it, options to it. Always going to be this tension between security or conservative security and.
I mean, I get what you're trying to do, right? But just the reality is extension headers get dropped, fragmentation headers get dropped, and TCP fast open doesn't work. Right? That's reality.
Problem. Extension headers get dropped sometimes. Loss rates are not nearly as bad as you would think. hop options. No, I mean, some of the extension headers said 90% on the internet. So they actually work most of the time. But working most of the time on the internet is equivalent to saying it never works. Because as a user, I don't know. Now, there's other things here. Like I said, I would love to have the grand map. You could actually take this grand map and feed it back into the sender, so the sender could actually know whether to send extension headers. You could do happy eyeballs. But it all comes back to the same thing. And it's just a fundamental problem we have on the internet is least common denominator rules. How do you overcome the least common denominator? You can make the argument IPv6 success rate hardly impressive on the internet still. What are we at, 50%?
Almost.
After 30 years?
Almost.
Come on. So this is life. This is how the internet works, right? There's no flag day. I can't just turn a switch and turn everything back on. So it's not that I'm trying to change the world to use these things. What we're saying is, can we save these things to make, for those who want to use them, can we actually make them useful?
Right. I mean, if you're focusing for like in data center use cases, that's a very different thing. That's viable, right? But
it's all applicable. This is another interesting trend in the IETF that people have strong opinions. So some people think you should take IPv6 and fork it and have an IPv6 in the data center. And in fact, the segment routing guys, some of them think SRv6, which is an extension header and IPv6, is actually its own network protocol. And they even arguing that they should have their own ether type, which would make sense. So some people actually think you should fork this. Argument becomes exactly that. Oh, we can do whatever we want in the data center. Problem becomes is the whole foundation of the internet and IETF was we developed protocols that are supposed to work everywhere and be interoperable. So again, we just have this tension. So my opinion is, yes, extension headers make the most sense within a data center. IOAM, SRv6, they're really not useful on the internet. But I don't think it's worth it to fork IPv6 and create this data center IPv6 with its own trajectory, because then interoperability becomes a big issue. So yeah, I mean, wish it was an easy.
Just an observation that IETF loves to make things extensible and complex, and then people that actually do the implementation come along and like rip out all the extensibility to make it actually implementable and secure and safe and extension headers and
IETF
fragmentation headers.
Complaining that Linux is violating all their RFCs. It's really fun living on both sides of this world because you see one side complaining about the other. It's fun. But yeah, some of this is IETF's problem. They created protocols that were way too. That's a common trend.
IPv6 is very hard to implement.
It was ambitious. Did we really need 128 byte address? Anyway,
So isn't the real problem that you don't know how long your tethers are before you started to parse it? I mean, if you would know how long the header chain is, you can check, does it fit in my TCAM?
yeah,
then you can decide parsing it or not.
That's actually gets into a different type of problem that I'm specifically looking at. We have this idea of variability and variable length headers. The only way to do it is to parse it. I don't know if I can, say we're looking for a specific hop by hop option. If I have 10 options, I have to follow each one. I have to look at the first, look at the second, look at the third. It's TLVs. TLVs, super flexible and super expressive, but they're miserable in actually processing. Hardware hates them because they can't parallelize this processing. So that's why the vendors That's why they didn't want to support IP options, because they're miserable in hardware. They're not exactly a playground in software either. At least in software, we can write a for loop to process them, but the hardware guys, they're like, I need something. I can't process a list of extension TLVs in 5 cycles. I need 100 cycles. So it's inherent, but it still comes down to the fundamental question: what are you giving us an alternative? The alternative seems to be don't have a protocol with extensibility. Then you don't have a protocol with extensibility. Or the other alternative is do some hacks. People are putting stuff into TCP or UDP options, but in the end of the day, they have the same effect. And there's also this other nice thing. If you write a protocol in plain text, regardless of what level it's at, yeah, somebody on the network's going to look at it. Oh, they change it. So fortunately, TLS is preventing people from inserting their own ads, but this is just so true at every protocol layer. So one of the reasons why I'm advocating we should be encrypting everything beyond the network header, and people would try to decrypt that.
This is more a curiosity question, and I'm, apologies if it's kind of a little naive, but if you're doing QoS using extension headers, is there potentially like net neutrality implications behind that, or anything in that domain?
Neutrality?
Well, I mean, as in like if intermediary boxes can see these things more easily versus, or my okay, no, sorry, naive question. Sorry, naive question.
Isn't it the Chevron case and net neutrality in the U.S.?
Sure. It's just again, I figured.
I don't know. It's kind of politics.
No,
you know what? I view it this way. They're politics, business case neutral. Having the ability to do something is not the same thing as saying it's for good or for bad. And we know that there's actually certain, I don't know if countries are doing it, but certain elements in countries that are doing things like inserting extension headers in packets on the fly so that they can tag them. We can't prevent it. They're not supposed to do it. Yeah, there are nefarious use cases for this. Security doesn't become interesting.
I'm missing another point from being brought up here, which is that the fact that extension headers are getting dropped is because there are implementations like Linux who will follow them down to 700 bytes or whatever. So Linux itself is part of the problem because it makes firewalls have to drop extension headers in order to prevent denial of service attacks against Linux hosts. So we need to fix this in order to, at some point, have firewalls not have to drop extension headers anymore because we're not susceptible to that anymore. Sure, that means we need to do it now so we can use them in 30 years.
That makes an assumption, which I will argue, that firewalls are for the benefit of the end host.
It doesn't necessarily mean that the firewall is for the benefit of the end host. It means that it's argued to be for the benefit of the end host.
So we are, yeah, I mean, we fix it. If we fix the problem, if we show usefulness, then the argument gets stronger. Also, I don't know if Nalini's online, Nalini, but one of the things that he's been doing is looking at some of the operators and some of the vendors that have been dropping extension headers, going in and finding out why, and asking them. In some cases, it seems like it's more of a bug than anything. So it's easy to make the decision, right? So nobody's using these, turn them off. You can make that decision 10 years ago. Now getting these guys to revisit that decision, sometimes it's a lot of work, sometimes maybe it's not. I mean, if we give them a good argument. So, but I sympathize with them on one side because they, especially with hop-by-hop options, I do believe they have an interest to prevent attacks on their network. I think their argument that they're protecting end hosts tends to be pretty flimsy, but I'm willing to accept that they can protect their own network. So I'll assume that there's some value there. How do we address that argument and undo that a mindset? It's work. I mean, none of this happens overnight, but that's the internet. It happens overnight. I think the critical thing here is we just need to not drop it, and we just need to keep pushing the envelope forward. IPv6, I've been following that for 30 years and kind of making traction now. So sometimes things just take long, but it's a good point. Yeah. Lenny, are you online?
Are you talking to me, Tom?
I think I am. Are you online?
Yep, I'm here.
Do you have any comments? Maybe can you share a little bit about some of that work you were doing? Help I guess the operators fix some of their issues.
Ugh. Well, okay, all right. I was trying not to, get on my soapbox here, but if you're asking, soapbox, here I come. So we've done some testing, and some of the things we found, basically, it's that, people are like, oh, people are, dropping them in the middle of the path, God knows what, or who knows, we can't ever figure out where they're being dropped. Well, we did a lot of testing, and it seems like by and large, I'm not going to say we've done entire testing of the entire world, but by and large, it's at the endpoints. By that, I mean, like, it's the cloud vendor and or the CDN who's dropping it. And because we put up just a raw server, not intermediated by anything. And you know what? It worked all over the world. Seattle to, Santiago. I mean, all over Singapore worked. But the minute you stick it behind something, and one CDN vendor, we found a bug, they admitted it and they fixed it. Another CDN vendor did not admit it, but they fixed it. Fine, I don't care. Don't admit it. There's one cloud vendor who does an excellent job, passes everything quite correctly, and I will name them because they do an excellent job. AWS. Everything goes back and forth. Other large vendors, other large cloud vendors who will go unnamed, do not do such a great job. So to me, frankly, it's like if there's a handful of people, 5 or 6, if they would get their act together, this situation would change dramatically. Okay, end of soapbox.
All right, well, thanks. Thanks for your work on that too. All right, any more questions? All right, well, thanks everyone for participating, and have a good Netdev.